All right, so have a nice day. This will be another video for the Fibonacci search algorithm. So when we say Fibonacci search, this is a comparison-based searching algorithm for sorted arrays that we are using the Fibonacci numbers to determine the probe position rather than dividing the array into equal halves as in binary search. In this case, by the way, we will be going to deal with the process, how we will definitely work then, and of course, there will be specific values for the Fibonacci that it will really takes a lot of time for you to manage this, but however, I'll be going to really illustrate this to you in order for you to really understand how does it work then. So this method is beneficial for large arrays and can be advantageous in systems where the cost of arithmetic operations is significant or where network access patterns matter. So in this case, this will really be technically easy for everybody because in this implementation you could easily find the specific element. Just give me 1 second. Okay, so let's actually continue then. It is somewhat efficient and can be better than binary searching systems where the cost of computing division and multiplication is expensive because the Fibonacci search uses only addition and subtraction. So in this case, actually, there will be a lot of thing that you will definitely process with because you will begin to calculate the Fibonacci M, Fibonacci 1, Fibonacci everything, the Fibonacci, and there will be a specific rule that you will be going to base that on. I'll be going to give you the rules that you have to follow in this video as well. So in this case, there will be the steps that you have to really go through the process. That this will be the basis that you will begin to base with as you go along. So in this case right now, you have to find the smallest, what do we call this one, Fibonacci number greater than or equals to the array size. Then initialize the offset to -1. So the offset, this will be the basis that you will begin to have with in the process. So first thing first, it will start in the negative one as you go along the process. Then while your f of m or the Fibonacci is negative 2, I mean, is equals to 2 greater than 0, we'll begin to deal with that later on. If only one element remains, compare it with the target, and if not found, return an successful or a negative one. We'll begin to uh, take it one by one. So finding the smallest here, Fibonacci number greater than or equals to the array size f of m, and keep track of f minus 1, minus 2, so you will begin to base everything. So you have to pre-compute the Fibonacci numbers needed to cover the array, actually, length for each division or for efficient division. You will definitely matter in that case as well. So definitely right now, in this case, I'll be going to walk you through the process later on in the next video for the example for this one. So that is definitely basic, and that will be the basis in that there will be calculation as well in the next thing. So let me go ahead and proceed. Initialize the offset to -1, indicating the start of the array. So offset helps to track the eliminated part from the front of the array. So definitely class, in this situation, and this will be actually helpful for you to calculate the what we call this one, the searching technique, especially for this offset, because you will set that one where we're able to stop earlier, and you have to step by step the process. I'll be going to illustrate to you the step by step for this one later on. And while your f of m is equals to 2 greater than 0, continue the search until the Fibonacci number becomes small enough to check the element, of course, directly. So we will begin to illustrate that as well. there will be a specific rule that I will be going to give you. That, for example, if your Fibonacci M, if it is what do you call this one, if your pay rate of it is less than or greater than, there will be specific rules that you have to follow then compare the target with the element at index mean offset plus fm minus 2, then comparing that into the n minus 1. So therefore in this one right now plus this will be the formula that you will be going to use in order for you to keep track those implementation and then check the current probe position without exceeding the array bounds. So this will be helpful for you to check if this will be in this calculation, you will be going to offset the offset then plus the fm minus 2. That is the result. What will be the result for that one? That in that specific result, you will try to check if that specific element in that value that you were able to found or I mean achieve in that calculation, you will compare that in n minus 1. N minus 1, that means to say that your number of element in the array minus 1. So that is 0 to n. Exactly. Now, in this case here, if the target is less, move the range to the left subarray. You have to update the FM, the F minus 1, FM minus 2, the everything. Then following the rules as well, the implementation. Shift the surge to the left side by reducing the Fibonacci numbers accordingly, depend on the situation best. If the target is, yeah, that is definitely one that you will be today's with. If the target is greater, move the range to the right subarray and update the offset and Fibonacci number. We will be going to update the offset if the target is greater than the value, if the target is greater than the current value that you have right now. Say, for example, the target that you were able to, the first shock, for example, in your current calculation, if and only if that this here, for example, you were able to find the specific element at 3, index 3, then your target is in the index 5. So therefore, you will be going to update your offset in 3. Of course, that will be the basis. Shift the search to the right side by moving the offset forward and adjusting the Fibonacci number. So we'll be going to illustrate that, of course, already. If a match is found, return the index, and if the element matches the target element, immediately return its position. Of course, that is technically what will happen if you were able to found the element in the given position that you were able to calculate using the formula. You have to return the value, of course. And if only one element remains, compare it with the target, handle the case when the search narrows down to a single remaining element. So, of course, you have to follow the same procedure. And if not found, return unsuccessful. If the entire search completes without finding the element, report that the target is not recovery. Or of course, definitely you will be going to put right there -1 as that will be the implementation if you were not able to successfully find that given element. Now, for initialization, this will be the basis that your Fibonacci M it will be the smallest Fibonacci number greater than or equals to the size of the array. Say, for example, later on, Fibonacci sequence that is basing with a 0, then 1. 1 plus 1 is equal, any, the F0 is 0, then F1 is 1, F2 is 1, and afterwards 2, then 3. 1 to 3, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, then 5 plus 3 is 8, then 8 plus 5 is 13. So that will be the basis that we'll be going to deal with later on. So for example, your Fibonacci number, I mean, your array is absolutely 13 only. So therefore, you will stop in your Fibonacci in a 13 as well. If you do have specific data that consists of 8 elements, so you will be going to use the 8 only. If your element right now is having the 16 element, you will be going to base the 8 plus 13, that is 20, wait a minute, 13 plus 8 is Okay, 13 plus 8, 21. So 21 will be your basis for the Fibonacci M. So technically, we'll begin to illustrate that later on. If the target is greater than the value at the probe index, that will be the rules, and the target is less than, and the Fibonacci 2, that will be the basis later on. I mean, so we'll begin to technically step by step the process. So if the target is greater than the value at the probe index, Fibonacci M is equal to the Fibonacci 1. Fibonacci 1 is equal to Fibonacci 2. Then Fibonacci 2 is equal to the Fibonacci M minus Fibonacci 1. If target is less than the value at the probe index, Fibonacci M is equal to Fibonacci 2. Fibonacci 1 is equal to Fibonacci 1 minus Fibonacci 2. Fibonacci 2 will become Fibonacci M minus Fibonacci. We'll begin to illustrate that as well in the implementation already. So the time complexity that you'll begin to base here, the best case is definitely constant time. The target is found in the first comparison, meaning that you were able to find in the first search already. Average case is logarithmic events, similar to binary search. The array is divided using Fibonacci numbers, not in half, but roughly in golden ratio. That means to say that in your average case, you're able to technically do a minimal process that you were able to find already that given position. In your worst case, that is logarithmic event as well. Even in the worst case, the number of steps is proportional to the number of Fibonacci number, which is less than equals to the n. So technically, we're able to do a lot of process, and that is logarithmic cases as well. In space complexity, that is constant time because we are only having a constant number of variables that we like the Fibonacci numbers and offset are used no recursion or extended data structures that being implemented in this case. So you're not using a lot of spaces actually. So that will be the steps, then time and spaces complexity as well as the description. And we'll begin to illustrate this in the next video, the example. So see you in there.